In this video, we are going to state Euler's theorem and Fermat's theorem. In the previous video, we have discussed about Euler's phi function. And now, after having sufficient knowledge of Euler's phi function, we are now able to state the Euler's theorem. So let me state the theorem, Euler's theorem. So let a be an integer and n be some positive integer. N is also integer, positive, such that a and n are relatively prime, means the GCD of a and n is 1. Then, according to Euler's theorem, a raised to phi of n will be congruent to 1 modulo n. In the previous lectures, we have defined what is meant by relatively prime numbers, means the GCD is 1. Then we have defined Euler's phi function, what is phi of n, that we have defined in the previous videos. Then we have also defined what is meant by congruence equations, a congruent to b. What is the meaning of that? That we have defined, and we have all combined all the things now, and we have put into together in Euler's theorem, right? Now we know that if n is prime, if the number is prime, so if I take p to be prime number, say, and I take GCD of a and p is 1, I'm taking a such that GCD of a and that p is 1, then or how will this Euler's theorem start looking like? So it will look like a raised to phi of p. The place of n is now taken by this prime number p is congruent to 1 modulo n. But I know that if p is a prime, then phi of p always comes out to be p minus 1. This is what we have discussed in the video of Euler's formula, Euler's function. So this means that a raised to p minus 1 is congruent to 1 modulo p. So this special version of Euler's theorem we call as Fermat's theorem. So this is your Fermat's theorem. So let me just recall what is Euler's theorem and what is Fermat's theorem. Euler's theorem in general tells us that if a and n are integers such that they are relatively prime, then a raised to phi n will be congruent to n 1 modulo n. So this n can be any number, n can be a composite number. So n is any number you are allowed to take. But if you choose n particularly to be a prime number, then I should write a p here. If we choose n to be a prime number, then we know that phi of p has value p minus 1. So phi of p will be replaced by simply p minus 1, and this modulo n will now become modulo p, and this theorem we will start calling as Fermat's theorem. Fermat's theorem is just a particular case of Euler's theorem, right? So once I'm sure with the Euler's theorem, we can immediately tell what is Fermat's theorem. Just put the n equal to some prime number, and phi of p will be equal to p minus 1. So I hope this is now clear what is Euler's theorem and Fermat's theorem. Let's look at some simple application of Euler's theorem. Okay, so let me just take a simple exercise. So if we divide say 4 raised to 37, this is a large number, by 7, what is the remainder? What is the remainder? So pictorially what comes into my mind, that 4 raised to 37 is a very, very large number. It's a very big number, right? And this 4 raised to 37, I'm going to divide by which number? I'm going to divide it by 7. Then I will get some quotient, which will also be a very large number, because I'm dividing that large number 4 raised to 37 by 7. So the quotient that I will get will also be very large number, but the remainder that I'm going to get will not be a large number. It will be a small number, because the remainder is always greater than or equal to 0, and it is less than the divisor. It is less than 7. So remainder will be between 0 to 7. So what are the choices for remainder? So remainder will be 0 or 1 or 2 or 3, or it will be 6. It cannot be more than 6. And this remainder we want to find. Okay, so I'm going to use Euler's theorem to find the remainder of this particular division. Okay, now what I will do is I'm going to divide it by which number? I'm going to divide it by 7. So I'll say choose n equal to 7. So who is n? The one with whom I'm going to divide. Okay, so n is 7, and choose a equal to 4. Why? Because I have 4 raised to 37, 4 raised to something. So it is looking like a raised to something. So my value of a will be equal to 4. In Euler's theorem, we have a raised to something, and in my problem, I have 4 raised to something. So I now understand that a has to be equal to 4. Is the GCD of 7 and 4 equal to 1? Are they relatively prime? Yes, the GCD of a and n is the GCD of a and n is 1. So this means by now I'm eligible to apply Euler's theorem. So by Euler's theorem, I can say that a raised to 5 of n is congruent to 1 modulo n. Let's put the value of a. How much was a? A was 4. 5 of n was 7. So n was 7 is congruent to 1 modulo n. N is 7. But we know that 5 of 7 is 7 minus 1, which is 6, because 7 is a prime number. And we know that phi of p is always equal to p minus 1, right? So this means that 4 raised to phi of 7 is 6. So phi of 7, I'm evaluating it as 6 here, equal to, is congruent to, 1 modulo 7. 4 of 6, 4 raised to 6 is congruent to 1 modulo 6. Now, which power of 4 do I want? I actually want the 37th power of 4. And that I'm going to write. Let me just look at the question back. Do I need the 37th power of 4? Yes. We need the 37th power of 4. And currently we are struggling with which power? We are at 6th power. So what I will do, I will just take 37 and divide it by, I'll just take 47. So sorry, 37th power, and I will divide it by this number 6. And I know that 6 is 36, and this is equal to, this is 1. 37 is actually what? 37 is actually 6 into 6 plus 1. So this 6th power is already here. The 6th power is already here. So I need one more 6th power and one more power, right? So how will I do that? So I'll say, so taking 6th power, so I will reach to 4 raised to 6 raised to 6. I will taking 6th power on both the sides is equal to 1 raised to 6 modulo 7. Now this 4 raised to 6 will become 4 raised to 6 raised to 6 will become 4 raised to 36. So we are close to 37 now. And how many powers are remaining? Only only one power is remaining, right? Which is congruent. No, 1 raised to 6 is 1 itself, so that will not change. And now I'm just one powerless, so I will multiply both sides by 4. Now we can multiply, no need to take a power of anything. So multiply by 4 to both sides. So I will get what? So 4 raised to 36 into 4 is congruent to 1 into 4 modulo 7, which is 4 raised to 37 is congruent to 4 modulo 7. Okay, what is the meaning of this particular line? The meaning of this particular line is that if I take 4 raised to 37 and if I divide it by 7, I will get a quotient, and the person who is here is nothing but the remainder. So who is the remainder in our problem? The remainder in our problem is 4. So remainder is equal to 4. You see, we already knew that the remainder will be less than 7 and it will be greater than or equal to 0. So 4 is a number which is less than 7 and greater than or equal to 4. So this is how you actually find the remainder using Euler's theorem. Okay, in the next video we will see some more problems which are based on Euler's theorem. So in this, so similar problems you can now do by taking a number, raising it to some power, and then dividing it by something, and then finding the remainder. Only one condition you must remember is that whatever two numbers a you take and n you take, their GCD has to be equal to how much? The GCD has to be equal to 1, and then you can sketch problems on your own. For example, if I take a equal to 5 and if I take n equal to 11, now I know that GCD of 5 and 11 is 1. So I can create a problem of my own. I can say 5 raised to something is divided by 11, and I'm interested in finding the remainder. So take this sum to be a big number, say take this 103 or something like this, and try to solve this problem. If 5 raised to 103 is divided by 11, what will be the remainder? I can do this problem by Euler's theorem because I know that the GCD of 5 and 11 is 1. So obviously I can apply Euler's theorem. In the next video, we will see some problems of finding the last digit using Euler's theorem.